Hello, dear students. Welcome to the Quantum Guru. Let's see this question from IIT-JEE Advanced 2020. Shown in the figure, there is a semicircular metallic strip that has a thickness T and resistivity rho. Inner radius is R1 and outer radius is R2. Voltage V0 is applied between its end and a current I flows in it. In addition, it is observed that a transverse voltage delta V develops between its inner and outer surfaces due to purely kinetic effects of moving electron. Ignore any role of the moving magnetic field due to the current. Then, which of the following four options, there can be more than one option correct, are correct? So basically in option A, about the current is asked, and then option B and C it is asked whether the outer surface is at higher potential or inner surface is at higher potential. And then in the option D it is asked whether delta V, the transverse voltage, is proportional to square of the current or not. So to find A, first we'll find the resistance of this metallic strip, and for that let's go to the next page. So this was a diagram given in the question, and this is a 2D diagram. The thickness of the strip is T, so in 3D it will appear something like this. So here I've tried to show the thickness of this metallic strip, something like this, and now this thickness is T. Let's take an element of radius R and thickness dr like this. Suppose this is the element, it has a radius R and thickness dr. So we would like to find the resistance of this element first. If I straighten this element, this will simply become a rectangular slab like this. Let me show it here. This will become a rectangular slab of length pi r, radius is r, half the perimeter is pi r, and its thickness, this thickness is T, and this width is dr. And the current, suppose the current in this element is di. On straightening, this current will go like this. This is di and this is ti. So resistance of this infinitesimally small element, let me write dr. This dr is equal to rho L by area of cross section, rho L, that length is pi r, and divide by area, that area dA. This area is this area dr into T. This is the cross section area. Through this cross section, current is crossing. So divide by T into dr. Potential difference between the ends of this element is this V0. If I take any other such element like this, any other such element like this, so still in that element potential difference is V0. So all such elements are in parallel combination because potential difference is same. So resultant resistance would be like a parallel combination. The if the resultant resistance is R, so 1 by R would be the summation of all 1 by drs, because the variable is continuous. So I can write this is equal to integration of 1 by dr, and putting the value of dr in this integration. So that will be rho pi r, and t dr will go in the numerator. Limit of integration would be obviously from R1 to R2. And if we integrate it, we are going to get T by pi rho will come outside, dr by r will become ln r, and putting the limit, we will get ln r2 by r1. So resistance of this semicircular metallic strip will become pi rho by T and divide by ln r2 by r1. So current I will become potential difference divided by resistance. So potential difference V0, resistance is pi rho, and T will go in the numerator, and ln R2 by R1 will go in the numerator. So this is the value of current that we are going to get. And let's see in the option A. And the option C is the same thing that we've got. So option A is correct. And now, suppose this is a free electron moving in this element. The current is di, so obviously drift velocity of this electron is, say, vd. This is moving in a circle, so it needs some centripetal force for the circular motion to happen. And from where the centripetal force come? In the question it is written that neglect any magnetic effect. So obviously the force that this electron will experience will come because of the electric field, the transverse electric field. For the circular motion, this is the center, and it needs to have a centripetal force along this direction. And this centripetal force can only come if we have a transverse electric field in this direction, like this. And because of this electric field, this centripetal force, the net force on the electron towards center, will become E into E. So that is one thing. Now, because of this electric field, what we can see that because electric field is in the outward direction, and we know that in the direction of electric field, potential decreases. So there will be some positive charges here, positive, 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 like this. And with respect to these charges, there will be some accumulation of negative charges here. So what we can say that the outer surface will be at lower potential compared to the inner surface because the electric field is in the outward direction. So we can get one more option, and that is the option C. So option C is that says that outer surface at lower voltage than the inner surface. Now let's see the option D. For the circular motion of this electron, we can write the equation for the circular motion. Fc, the centripetal force, is equal to mass times the centripetal acceleration. The centripetal force is coming from the transverse electric field, and its magnitude is going to be E into E. And centripetal acceleration will obviously be Vd square divided by R. R is the radius in which that electron is moving. So Vd is the drift velocity. So I can bring this E here. So this will come here, and that will become mvd square divided by ER. So for this element, we can write dE. Di, current, is equal to Ne, and the area of that section into Vd. This is I is equal to Ne a Vd. N is the number of free electron per unit volume, that is the free electron density, is the electronic charge. D is the area of cross section through which the current is flowing, and Vd is obviously the drift velocity. And for the all such elements, potential difference is V naught. So this Di is equal to V naught divided by resistance Dr, and again Ne dA into Vd. So once again, dr that we had written just before, that will be rho into length pi r and divide by area dA. I could have written the complete area dA to be T into dr, but because there is dA here, that dA is going to be cancelled, so no need to write that much. So here we are going to get dA cancelled. So we've got Vd is equal to V naught divided by rho pi Ne and R here. So putting this value of D into this equation 1. So that would give me E is equal to M divided by ER. I will put there. Yeah, okay, let me put first, and this Vd is equal to V naught divided by rho pi Ne R and whole square. So because we have to only tell how this varies with current, so I am taking all the constant thing put together and to and into another constant. This m is a constant, e is a constant, rho is a constant, pi is a constant, again n is a constant, and e is a constant. So clubbing all these constant into one single constant, say k, and that will become v naught square, and divide by only one variable with it. There is r and there is r cube. And we had written that v naught is equal to I naught r cube. So this v naught is proportional to that I. So I can write this another constant c into I square and divide by r cube. And magnitude of this electric field would be dv by dr, and dv by dr is equal to c I square divide by r cube. So dv is equal to c by r cube I square dr integrated with suitable limit. And here the limit of integration is going to be r1 to r2. And if I integrate it, I'm going to get this magnitude of potential difference to be I square is a constant, and that c by r cube integration will become another constant. So let me write that another constant as a some alpha, and that is alpha into I square. So overall I can say that delta v is proportional to I square, and that is, I think, option D also. So option D is also correct. So we've got options A, C, and D correct in this question. Thank you.